Okay, so today I'm going to be going over correlation. And correlation is really a measurement of strength of linear association. Mostly, almost exclusively, what we would be doing is really interpreting and talking about correlation. Today's lesson is a little bit about the mathematics, which is actually pretty cool. But you don't need to worry, you will not be calculating it by hand, but I am going to show how to do it. Correlation measures the strength of a linear association, and it's of two quantitative variables. So sometimes students want to say two things are correlated when we're talking about categorical. Correlation is a mathematical quantity, and it only can be calculated for two quantitative variables. The calculation looks like this. We use the variable r for correlation, and it looks like 1 divided by n minus 1. So basically this is an average. There's a correction here. This n minus 1 is not an exact average because we lose a degree of freedom is the statistical lingo for that. And then we sum this mess over to the right here. I do want to break down what these exactly are because it looks a lot worse than it is. Here it says x, and those are all of my x values in my coordinate pairs. When I have bivariate data, I end up with like x, y pairs, and I graph them. So I take all of my x's and I subtract the mean of the x, and I divide by the standard deviation of the x's. I do the same thing for the y's. Take each y, subtract the mean, divide by the standard deviation. What these two really are, they're really measuring how far from the mean. That's sort of what we always want to know is like, well, how far is it from typical? And then I sort of have this conversion that I don't want the units of whatever data set I'm using. So I want to sort of standardize it. And I standardize it by dividing by the standard deviation. So then my measurement becomes a measurement in terms of how many standard deviations from the mean. We actually have a letter for this, and this is a z-score. This calculation, how far, subtraction, dividing by the standard deviation, this is like pretty much every statistical calculation out there. It's basically giving me a position in a standardized way I can understand no matter what units I'm using. If I know something is 3 standard deviations above the mean, it's like, whoa, that's really high. I don't care what units I'm using, I know that. Okay, so just breakdown of the math of what we do in this calculation. So basically there's going to be a shift. I have my XY coordinate, but I'm going to draw this line right here. This is the mean of X. I'm going to draw this one the mean of Y. And so basically what this is going to do is if I draw these two lines for any data set, any scatter plot, if I draw them through the mean of the X's, mean of the Y's, it's going to go right through the middle of my data. So if here I have this scatter plot, and there's like some scatter here. Overall, the trend is positive. Maybe I say it's a moderate. But so these two lines split the middle of that data. In this data set, if I was to look at what happens up here in this upper quadrant, these are above the x mean and above the y mean. So that when I multiply, and down here, these are negative. They're below the x mean, below the y mean. So for both of those, in those two quadrants, in quadrants 1 and 3, when I multiply those standardized scores, the distance from the mean, I'll get positive values. These are all above the x mean, above the y mean, so I multiply positive. These are both below and below. Two negatives, I still get a positive when I multiply those. So overall, the positives are going to win when calculating this correlation. Here, if I go the other direction, and again, this is, I would say, a moderate or moderately strong negative association. And there's kind of like only one here that falls out of that negative general trend. Because here, I have 1 negative, 1 positive, below the x, above the y, down here, and so I'm going to get that negative score. Down here, in quadrant 4, I have 1 positive, 1 negative, so that when I multiply those, I'm going to get a negative. So that the trend here is negative, my correlation is going to be negative. If I have a big blob, I have about the same amount above and below. These are positives and negatives. When I add them up, they're going to cancel, and I'm going to get something very close to 0, which is mathematically why this correlation calculation comes out very close to 0. Let's look at an example. So this is data taken from families. They were given a crisis, and they were given a score on how they could manage that crisis. And then they were also given a series of like questions and tests to come up with a family strength core score. And so here is a graph of that data. If I look here, okay, so if I'm looking at the scatter plot, I see a positive trend, but it's pretty weak right here. There's kind of a lot of spread, and then I also see this point way down here that's right on the y-axis. There was a family that got 0 on their crisis management score, so they really bombed that crisis. Their strength was okay, but bombed the crisis. So let's go ahead and write a description for this. So I would say there's a positive weak linear association between crisis management score and family strength. There's one possible outlier or influential point at 0 crisis management and 52 family strength. I use this word influential point because sometimes I'll have a point and it is unusual. Sometimes it can actually strengthen my correlation, and sometimes it can mathematically make it stronger, especially when it's very far away. So I use that word carefully. We're going to come back to that. Don't worry about saying that, but those are the words I'm using right now. So I'm saying it's an outlier or influential point because it might be actually influencing the correlation to be higher numerically than I would expect if I removed it. So notice here I have my context. I have the direction that's positive. I have unusual point or unusual feature. I have my form and then my strength. So I went through Duff's. Okay, so here I've got, I went ahead and this slide has the conversion, is that I took all of those scores and I did the conversion calculating the distance. So that first score, there was a 10 and the mean of my X's was 17.1, standard deviation was 7.475, and I found the distance. It was about a little less than half a standard deviation above. This one was like, you know, a half a standard deviation below. This one was like a little more than 1 standard deviation above. There's another video showing how to do this. If you have interest, you will not be doing this by hand. It is not required, but that's what these are. It's calculated by hand, then I multiply these. After I have them multiplied, then I add them up. I can see here in this product, there's a fair amount of positives and negatives. So that when I add this up and then when I go ahead and divide by 10 minus 1, that averaging, I get 0.4633. So it's below 0.5. So again, it supports that there's a weak correlation between those values. Mathematically, I think it's pretty cool that this calculation can give us such an accurate measure of how closely those points fall in a line, and that it is always between -1 and 1, which I think is cool. So some facts about correlation. This is more important than the calculating it by hand. So correlation does not care which is X and Y. I can switch X and Y. I'm just multiplying, and so it doesn't matter. R is not affected by changes in units. I talked about those standardized scores, is that since I'm measuring in standard deviation, it doesn't matter what units. R does not have units, it's just a more general description. Correlation is always between -1 and 1. -1 is a perfect line that has a negative slope. 1 is a perfect line that has a positive slope. Correlation only measures linear relationships. If there's a curved relationship, it will not measure the strength. And correlation is not resistant. It is affected by unusual points, like outliers and influential points. Some points can actually make the R higher than maybe it should be, and some points can make it lower than maybe it should be. Correlation does not imply causation. It measures association, but it doesn't say that one is causing an effect in the other. It frequently happens that 2 variables are highly correlated, not because one is causally related to the other, but because they are both strongly related to a third. That word right there, it's not casually. Be careful, that causally is different. It's implying a cause and effect relationship. So if I interpret the correlation, This is what our job is going to be. We're going to do a whole lot of practice with this next week, next class. But here's just a general little guide. I like this little visual. This first one, that's a perfect positive correlation, R equals 1. The next one, it's strong. Notice that it's got a positive slope. It's pretty close if I drew a line in there. R would equal 0.91. This one is a weak positive correlation. Again, the R is below that 0.5 level and it's at 0.48. Here in the middle, blob, and I get R equals 0. Weak negative correlation, R equals negative 0.48. And that's a weak negative. The strong negative, again, the other direction, negative slope, it's negative 0.91. And then a perfect line with the negative slope is R equals negative 1. Let's look at an example. So I have a scatter plot. This is city miles per gallon versus highway miles per gallon. And I have an R of 0.94. We will either be using Steplet to calculate correlation, or it will be given. You will not be calculating it by hand. In this example, if I interpret it, there is a strong positive linear association between highway miles per gallon and city miles per gallon. And there is a gap, and there are no vehicles kind of in the range of 41 and 46 miles per gallon. So again, I did my CDEFs. I've got context, direction, form, direction, unusual points, form, and shape. And I'd like to also point out that these two do not, one is not causing, the highway miles per gallon is not causing a change in the city miles per gallon. Both of them are related to an underlying variable of like vehicle type or weight of the vehicle, something else. All right, so I'm going to make a couple more videos that you're welcome to watch that are sort of extra. One is on how to do this in Staplet. The other is a little bit about Sheets if you want a little Sheets tutorial. And then on Monday you can expect we're going to do a correlation guessing game. All right, everybody have a great weekend, and I will see you next class.